So participants, now we'll be moving forward to our next session. This will be the second plenary talk. And for this, we would like to invite Dr. Vishesh Manjunath from Indian Institute of Technology, Indore. But before going forward with the presentation, I would like to give you a short, brief description for the Dr. Vishesh Manjunath. Vishesh has received his master's degree in 2016 in nanotechnology from VIT University, Bangalore. In 2017, he has joined Dr. Rupesh Research Group in the Department of Metallurgical Engineering and Material Science at the IIT Indore. His research interests include photovoltaics, thin film technologies, fabrication of optoelectronic devices, water splitting, electromechanism, visible and ultraviolet light sensors, and CO2 capture. He has published over 20 plus research articles and 3 book chapters in the respective fields that we mentioned. So, thank you, sir, for joining with us today. And we are interested. The floor is all yours. And please kindly start with your interesting talk.
So much. Screen is visible, right?
Yes, we can see it.
Just a bit noise. Okay. Thank you for such kind introduction. And I've been like, I'm to the other participants. I've just completed my PhD in IIT Indore with Dr. Rupesh Devan in Nano Architectures Research Group. Though we work on many fields for energy storage and conversion, today I'll be discussing about perovskite solar cells. And these perovskite solar cells recently have taken a lot of research momentum from 2009, 2008 when it was discovered. Then from 2013 till today, it's the research article, the count of research articles is crossed more than 5,000 research articles throughout the world. So this is a quite interesting topic. So let's actually look into it and discuss some of the things. So the outline of my talk will be including, we'll go through some introductions, classifications of solar cell, what are the performance parameter, how do you compare solar cells, what is perovskite solar cell, how did it evolve, what is the device architecture in the perovskite solar cells process, the working principle, the fabrication procedures, and some drawbacks of perovskite solar cells, and next we can conclude the talk, right? So coming into the introduction, so we should be aware why we have to work on like solar cells. What is the need of working on solar cells? So there is something called as terawatt challenge. So to run a simple laptop, you need around 1 watt of power. The a toaster, a bread toaster like shown here, might require another like around 1 kilowatt of power. To propel a plane, you require around 1 megawatt of power. And our nuclear reactors can generate around 1 gigawatt of power. But in the near future, for the world to actually, so like world will consume around 1 terawatt of power. So to actually provide this 1 terawatt of power, we have to employ around hundreds, thousands of nuclear reactors, which is actually not a safe and viable solution. So, however, we know if we cannot make hundreds or thousands of reactors, we can use the same nuclear reactions which is happening at a safe distance. So in the case of sun, there are again nuclear reactions, and it is at a pretty safe distance. And annually, like we produce around 4.6 into 10 power 20 joules of energy, and this is roughly 60 seconds of the sunlight which reaches the earth, if we can tap all these things. So it is very important to tap it efficiently. So tap the complete visible light or the spectrum or the complete energy coming from the sun, and convert it into useful energy, and we can actually solve this terawatt challenge. So when we talk about harvesting solar radiation or solar energy, there are different approaches to it. So there's solar thermal, in which they use the IR spectrum of the sun, where the solar energy is converted into heat, and this heat is used to actually generate steam out of a working fluid. And depending on the temperature, again, this solar thermal is again classified into three types: for your low temperature application, mid temperature application, and very high temperature application. When you talk about low temperature applications, we see it on housetops for normal water heating. We talk about mid temperature applications where you have mega kitchens where you need high pressure steam. And when you talk about very high temperature application, you actually propel or run a turbine. You generate so much of steam and run a turbine. So no audio. Hello, can you hear me?
Yes,
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 sir.
yes.
Yes, someone just told no audio. So in the high temperature application, you use the steam to run a turbine, and this turbine you can actually generate the electricity. Similarly, there is another technology in which people have started generating green hydrogen, basically by splitting water. And splitting water, you can do it in many ways. You can actually apply some small voltage of 1.23 volts, and you can split it. But however, the over potentials, what is required will be further can be reduced, or else you can use sunlight energy to actually split the water and produce a green hydrogen. Then this green hydrogen can be again stored, and it can be used to run an internal combustion engine, or even can be stored or processed into useful chemicals by the chemical factories, or even the green hydrogen can also be used to generate electricity by using fuel cells. But the most efficient out of all these things is like, or we can say the more important is solar cells, because solar cells is like it's a normal p-n junction diode. After when the irradiation is shined on it, it can generate electricity. It works on very basic principles of physics, and it can convert direct sunlight into electricity. Comparatively, when we compare the other technology, all these things, the weight of the solar cell and the amount of energy which it can convert is very high. So the high power to weight ratio is pretty high in solar cells. It can handle large scale very easily. You can make panels out of it. You can connect panels together. And recently, the solar farms are coming up even in India, where people are making solar plants, generating and selling back to the government, where they get double the money than what we consume. And one more thing, we cannot tell solar cells has zero pollution, but it has minimum pollution, because the waste, once the solar cell is ages after 15, 16 years, in case of silicon solar cell, how do you handle the waste of it? How can it be recycled? So that causes a small amount of pollution. So anyways, people are also working on recyclability of solar cells. So that is also an important point of view, right? So next, when we talk about solar cells, people have classified solar cells in different generations, like first generation, second generation, third generation, and some novel technologies. When you talk about first generation solar cell, people in Bell Laboratories use single crystalline silicons, and they formed a PM junction, homo junction, both in the meaning both your N type is also made up of silicon, your P type is also made up of silicon, and they used to generate some amount of uh, electricity out of it. However, this silicon technology, they started with silicon mainly of the reason of its band gap, which is around 1.1 electron volt. So when we see the solar spectrum on the right top side of the slide, the energy of the spectrum, the energy of the complete sun spectrum in the yellow part is around, it shows a black body spectrum of around 5,800 degrees Celsius. That is the spectrum of sun. However, when that spectrum enters into the atmosphere, there are attenuations. Because of these attenuations, you get some amount of, you can see the intensity of the radiation drastically decreases because of all this attenuation. So this is a 5,800-degree black body radiation, but however, what we get on a for the terrestrial application is drastically reduced at the sea level because of this attenuation from ozone, other molecules in the atmosphere and stratosphere and all these things. However, the main important point we have to notice is in the visible region, the area under this curve in the visible region has highest energy, like the highest content of the solar spectrum. It falls in the visible region. More than 70% of the solar spectrum what we receive for terrestrial application is in the visible region. So we have to. So people thought of harnessing the visible region. So around 800 nanometer, the visible region ends, and that 800 nanometer corresponds to the band gap of silicon, according to our Planck's equation, and that's the reason people started with silicon for the first generation solar cell applications. Then, however, uh, when they made all these things and they started getting efficiencies from cyclical solar cells, then they realized the cost is very high, because when you make single crystalline silicon, you follow a process called Cherboski process, where the temperature is required is like huge, and it needs a continuous power supply for it. So, in fact, in countries like India, we even today don't make we don't make silicon solar cells like for commercialization, because supplying continuous power for 24 hours, and in that process of making single crystalline silicon, even if there is a power drop in for 1 second, the amount of loss is pretty high. So that's the reason most of the even the giant companies in India are even not like confident enough of making silicon solar cells presently in India. So then, because to reduce the cost, again, people started making polycrystalline silicon, in which you don't need so much of energy and so much of money to make polycrystalline silicon. However, compared to monocrystalline silicon cells, the efficiency dropped in polycrystalline solar cells because of its grain boundaries and other interfacial losses and other recombination effects with both optics and your uh, what is electron recombinations. But this is presently this is one of the mature technology, but the cost is very high. So that's the reason the buyback policy in India. It's like if you make a solar farm of install panels and make a solar farm, the amount of money you invest and the money that time you break even, that money is 5 years. So the profit what you get is after 5 years. So to reduce the cost, people again shifted to second generation solar. So it's not the efficiency is higher. So people actually misunderstand this first generation, second generation, third generation novel technology. So from first generation to second generation, when we shift, it's not efficiency doesn't become higher. Efficiency actually drops. But the main concern is to reduce the cost. So in the second generation solar cells, like there are amorphous silicon cells. So people even in second generation cells, they didn't even stop using silicon. They started making amorphous silicon. The efficiencies further dropped, and when these cells are like usually made in thin films, made out of thin films, so it had a very good flexibility, and it was easy to package and transport, and it can be used in building integrated photovoltaics. Like they can stick it on windows, and they can make multiple devices on the windows and harvest the harvest uh, harvest sunlight. Then the CIGS solar cells, again copper indium gallium selenide solar cells. Here they formed a semiconductor out of these metals, and even this was a good light harvester. And but the main problem with CIGS solar cells, when you're using four different metals and trying to form a single phase out of it, controlling the phase is really a skill task. So that's the reason even today CIGS solar cells has also not been commercialized very well. And using the selenium sulfur in CIGS solar cell again increases toxicity. So from year to year, you're reducing the cost, but other problems were again increasing. So, but however, the main outcome of the second generation solar cells, where people started understanding that we can actually make solar cells which are flexible. You can roll it, and because of this flexibility and making it out of thin films, you can actually print it like a newspaper. You can do batch processings, you can do roll to roll fabrication, and you can actually scale up the technology. And then the latest third generation solar cells, here these are quite fascinating solar cells, because it's a simple division of labor concept. So we'll just look into that later. So in third generation solar cells, we have dye-sensitized solar cells, we have polymer solar cells, we have perovskite, we have quantum dot solar cells. In dye-sensitized solar cell, you make use of normal small organic or inorganic dyes, which will act as your light harvester. And you will have an electrolyte which will regenerate the dye. And the counter electrode and all these things, it will divide and it will divide its task. So every individual part of a dye-sensitized solar cell will divide its task and collectively work together. So this term is also called division of labor. We'll actually look into that. And however, compared to second generation solar cell, again, third generation solar cells efficiency is dropped. So here in CIGS solar cell, the highest efficiency people have achieved is around 22%. But when you case of dye-sensitized solar cells, the cost is pretty low. But the efficiency till now, highest efficiency achieved is around 13%. Then the polymer, to make it even further cheaper, people started making bulk heterojunctions with mixture of two polymers. So even these cells have lower efficiencies. Then we have quantum dot solar cells where we use multiple quantum dots of different shapes and sizes to harvest different part of the spectrum and collectively make it work as a solar cell. And these concepts is again dependent on our band gap engineering, the third generation solar cell. Then we have novel technology where you mix different technology because every light harvester has a pretty different band gap. So silicon cells is a band gap of around 1.1 electron volt. Like for example, polymer has around, like, depends on the polymer. If you're using particular dye, it depends on the what you're sensitizing the dye, and like semiconductor, what kind of semiconductors you're using, what dyes you're using, it depends on all those things. So in tandem technology, for example, people have made tandem solar cells with silicon as bottom cell and perovskite as top cell. And but however, we have to know the efficiency of these perovskite solar cells is right now are comparable to silicon solar cells. And we have to just understand we have crossed three generations and we have reduced the cost, and we have again gone back to the pretty high efficiency cells. So this is a quite interesting topic. So that's the reason in the last 10, 12 years, the tremendous amount of research has taken place in perovskite solar cells, and let's further look into it. So when we talk about solar cells, we have to analyze what is efficiency and what is not efficient, like what are the parameters we have to look into, even if you buy a solar cell or whatever it is. So we just works on a simple diode model. You give some light, you connect it across a load. So when you solve all this KCLs and KVLs and the equations at particular nodes, and you actually get this IV graph. Out of this IV graph, you can actually find out what is efficiency. So your efficiency is nothing but the amount of light incident to what you are getting out of it. So that is the efficiency concept. So whenever someone talks about solar cell, it's always about efficiency. And the voltage is also important because when you are using a particular load, you have to have the same voltage which the solar cell can deliver, so that you can get the maximum like extraction. If you can extract maximum amount of energy, then there's a terms called this current short circuit current, and they are fill factor. So this is NREL chart. So NREL is a laboratory in US. So these people actually maintain a chart and see how the solar cells have evolved over the time. So we have different kinds of cells. We have two junction cells, single junction cells, crystalline silicon cells, now thin film technology, emerging photovoltaics, everything. So when we talk about silicon cell started somewhere in 1977 in somewhere in Bell Laboratories in the US, and to reach a efficiency of around 26%, 25%, it has taken a time frame of more than let's say 35, 40 years. So we have different technologies similarly, which has taken some pretty amount of time for it to evolve and get some stabilized efficiency. So these are like around 46%, 44%. These are not from single junctions. These are with multiple junctions. So it's like a tandem technology where two or three solar cells are used in tandem to get the very high efficiencies. So here, when we zoom in at this part, when we look at this perovskite solar cell, which is like a red circle with a yellow filling, this year you can see it here. It's around 2013. It got some reasonable efficiency of around 13.4%. And around 2019, around 23.3% of efficiency is being achieved. So in just a matter of 10 years, this high efficiency was stabilized in perovskite solar cell. Today, in today's time, at 2022, the efficiency has actually gone to 25%, approximately 25% of efficiency, in the sense like the energy, the 1/4 of the energy from the sun is actually converted into electricity very successfully. And this big achievement was done in just last 12 years of time. So these are very robust material. Perovskites are very robust, and uh, we will see how it evolved and what are its features. So why this was possible? So when we talk about perovskites, it's a normal perovskite like AbX3 structure where like it follows this calcium titanate form, in which it is a body centered, face centered cubic. And these AbX3 structures, here when you see calcium titanate, all are inorganic structures. But when we talk about perovskites, perovskite has both organic and inorganic part in this particular structure. It follows the same perovskite structure. So in this, the A part, when you call it AbX3, the A part can be your organic cation, and your B part is usually inorganic, inorganic metal ion. Usually, sometimes you can actually, people started changing that. Then this I, we don't use, this is oxide perovskite, and these are halogen perovskites. So there is, it is either iodine, chlorine, some different compositions of iodine or chlorine. So when we talk about these structures are very well-known structures. The perovskite structures are very well-known structures, and these structures can be tuned very easily by replacing either of the atom if they can sit in this particular positions. So similarly here, you can actually remove this B and insert a C, which is having the same ionic radius, a little bigger or smaller, so that you can actually control the physical and electronic properties of this organic inorganic perovskites. So that's the reason this robust material was exploited by the researchers to achieve very high efficiencies. And when we talk about solar cells, the absorption coefficient is very important. So absorption coefficient is like how much amount of light it can absorb in a particular, for a particular thickness of material. For a similar thickness, the absorption coefficient for different technology is shown here on the left graph. When we see silicon technology, it's around from 1100 nanometer to 1100 nanometer. It can absorb around 200 nanometer, but however, its absorption coefficient is lower as compared to CS3 and STPBI3, which is organic inorganic perovskite. And we have CIGS, which is also similar to perovskite, but it harnesses a different part of the spectrum. So perovskite is harnessing up to 800. So CIGS is around like harnessing a different part. Then we have cadmium telluride and different technologies. So compared to all these technologies, silicon solar cells, perovskite solar cells are also competent enough to deliver, to absorb light and absorb light and harvest the incident energy. Then methyl ammonium lead iodide, when they take the reflectance, so similarly axial reflectance, we can see that it can actually reflect, it actually absorbs everything from 400 to 800 nanometers. So this is the exact spectrum we are talking about in our previous slides when we spoke about 70% of the incident sunlight. So this like it can completely absorb its 70% of the sunlight which is actually falling on the earth, and the corresponding band gap of around 1.55 electron volt this CS3 and STPBI3 possess, and the absorption coefficient is 10 power 5 per centimeter. Then again, comparing different technologies with Schottky quasar efficiencies. So this is a Schottky quasar efficiency for a single junction solar cell uh, for a terrestrial application. So this was a little bit older data. So this efficiency has now gone up to 25%. So when we see this curve, the main thing we have to understand is it's a bell-shaped curve. So the highest efficiency for terrestrial applications is around 33.4 or 34% for single junction. And in this bell-shaped curve, silicon falls in that particular region, and the gallium arsenide also falls in that particular region, and perovskite 1.5 electron volt also falls in that particular region. So now this part is actually moving up. However, for the silicon, the band gap is fixed. So if you have to increase the efficiency, you have to work on other texturing and other cells. here our perovskite is as a variable band gap. So you can either pull it here so that you can actually move to the maximum point, or you can actually play with it for depending on your application. So with this tunable band gap in the structure, so MAPB is again, see the organic part, this is the inorganic part, and this is the halogen part. So in this organic part, or when you replace this either organic part or inorganic part with SN and things like that, you can actually change the band gap. And you're replacing the atom and you're changing the band gap, and you can tune the band gap somewhere close to 1.2 electron volt. So it is almost somewhere near silicon cells. Then and then you can actually maximum efficiency you can achieve is around 34%. So the people have tried tuning the band gap of perovskites, and so this technique, people broadly classified this technique as band gap engineering, and choose the particular exact band gap where you can actually move towards the towards the maximum efficiency of short diffuser limit. So how did this perovskite solar cells evolve? So from it actually evolved from dye-sensitized solar cells. So we just have to understand what is dye-sensitized solar cell, and how it works. So actually it is nothing but impersonating natural process. So when you have a plant, you have roots, you have leaves. Again, leaves have chlorophylls, which is again dye, and you're giving some sunlight to it. So the chlorophylls part in the plant is to just collect the light, to absorb the light. The roots part function in the plant is to absorb water from the ground. The stem is again used for mechanical support. So similarly, when we see this dye-sensitized solar cell here, we have a transparent anode, you have a transparent cathode, right? And in this, you have coated a back metal contact, which is a platinum cathode. And we have a TiO2, which is a TiO2 like nanocrystals on which the dye is sensitized. So whenever and this is again filled with electrolyte. So whenever the light is actually when the light enters the dye sensitized solar cell, the dye's part is to create electron hole pair. The TiO2 will dissociate the generated electron hole pair, and this electron hole pair will move towards the FTO. In the meantime, to avoid the recombination, the electrolyte will regenerate the dye, and then the circuit will be completed with a platinum cathode. So this is the concept of dye-sensitive solar cell. So here the dye individually is doing its work. The TiO2 is individually doing its work. The platinum cathode and the electrolyte is individually doing this work. And here the people use liquid electrolyte. And since you use liquid electrolyte, this should be sandwiched in a sealed structure. And for physical application of this, when you put this dye-sensitive solar cell on rooftops, actually the surface temperature of solar cells on a bright shiny day reaches up to around 80-90 degrees during working conditions. So at 80-90 degrees, when you have a sealed structure which is filled with liquid electrolyte, the liquid tries to expand, and these seals will break, and the cells will actually disintegrate. So people thought, okay, why should we use liquid? So if it's causing this much problem, so people started using solid state electrolyte. So they started using a solid state spirometide electrolyte, and they called it a solid state dye-sensitized solars. Similarly, TiO2, then they used, they sensitized. Here it was sensitized, here it was a proper confined coating, right? And then the perovskite mesoporous structures. So here TiO2 is an N-type semiconductor, whereas here they used again Al2O3, which is an insulator. And this was actually possible because perovskite itself can absorb light, and it itself can dissociate electrons by itself, and actually allow it to be collected at the load. Then we had different porous p-n junction, porous perovskite p-n junction, then meso superstructures, then PIN thin film for perovskite. So we will look into this evolution in the next slides. So the basic thing here we like actually consider is the importance of solid electrolyte. So just by shifting from liquid electrolyte to solid electrolyte, we could solve big problem, and we could even achieve very high efficiencies. So First perovskite solar cell was actually in Japan by Miyasaka in 2009. So with the concept of dye-sensitized solar cell, he used TiO2 nanocrystals and sensitized these TiO2 nanocrystals with methylammonium lead bromide and methylammonium lead iodide. So the IV characteristics here with this data, he got efficiencies around 3.13% and 3.81%. And after this in 2009, people told, since he was using liquid electrolyte, he just mimicked the dye-sensitized solar cell. So instead of dyes, he started using perovskite. He sensitized TiO2 with the perovskite dyes. So though he got so much of efficiency, people told you're again using liquid electrolyte, and the devices failed within, like, after 10-15 measurements, the devices failed in 2009. Then for 5 years, the research was like almost for 3 years, the research was stopped on perovskite solar cell. Then the next paper which came out on perovskite of solar cell was from Grazel. So Grazel, Michael Grazel is like, is even today considered as god of dye-sensitized solar cell. And with this effort and with his experience with dye-sensitized solar cells, he actually used perovskites, and he used TiO2 infiltrate perovskites in the TiO2. He didn't sensitize, and he used a solid electrolyte, a spirometer, and with gold as counter electrode, he was able to achieve around 9% of efficiency, and 500 hours of stability was achieved. So once this solid state thin film evolution of perovskite from sensitized perovskite, this captured a lot of people's interest after 2012, and then the solar cell started evolving. Then this is another big name in perovskite solar cell, Henry J. Snaith. Same, what did he do is, like, why to use only TiO2? So can we try with insulating Al2O3? So here they noticed from this paper was, they noticed that when this TiO2 is dissociating the electron hole pair, the electron passed through the TiO2. However, the perovskite had a capability. It is not only a light harvester, it can also transport electron on its own. And this finding was also very big. And in this finding, people started understanding the robustness of perovskites. And with the Al2O3, with the insulating scaffold, around 10.9% of efficiency was achieved by Snaith. Then people came to know, okay, if the perovskite can actually transport, if perovskite can transport electrons on its own, so can it transport holes also? So holes, so people started using without HTL. So there is a problem was, like, whether we should use liquid electrolyte, solid electrolyte, and this paper again from Grazel told, don't use anything, it's fine, perovskite even then will work. And this was possible because the diffusion lengths in perovskites and their combinations is around 1 micrometer for electron and hole. And this is almost matching each other. So we call it as ambipolar transport, where it can transport electrons and hole for around 1 micrometer of distance without recombination. So this and removing a HTM layer, which is very expensive, drastically can also further reduce the cost. So these were the outcome of this paper again in 2012. Then the evolution is like from 3.81% to 9% to planar heterojunctions to in 2018 around 23.3% to presently around 25% of efficiency is achieved with perovskite solar cells. So in this, the sensitization and non-sensitization and the mesoporous concept, in this, what people actually tried doing, they tried to mimic the dye-sensitized solar cells. So they used TiO2 nanocrystals, and when there is electron hole pair generation, the electron used to dissociate at this particular junction or at the interface of TiO2 and the perovskite, and the electron was transported through the TiO2. But people then realized, because of this because of this very high diffusion length of this perovskite itself, there is no need to use any such structures. There is the perovskite itself can transport both electrons and holes, and it can actually dissociate them. So the people started using uh, exact film kind of structures, and this kind of models is like similar to silicon solar cells, and presently really high efficiencies comparable to silicon solar cells are being achieved with this particular both the device architectures. And when we talk about advanced device architectures, then people started telling why to use metal contacts. Metals will again increase the cost. People started making carbon-based contacts, and depending on the structure, whether it is NiP or N, because TiO2 here it's a N-type metal oxide. Perovskite can act as both N-type, P-type, and intrinsic, depending on where it is sandwiched or where the junction is formed. So they call this regular NiP structures. Then they call it as mesoporous regular NiP structures. Then we can also make PIN structures. So people started using even polymer HTLs. So it was like PI and ETL. It's again polymer ETL, C60. So these structures were made. Then again, P dot, PSS. So different polymers and things. So this all shows all this finding shows that the robustness of this organic inorganic perovskite. So you take it, you simply make a device and sandwich or not sandwich or use HTL or ETL or just form a junction for a solar cell, and it can actually work as a solar cell, and it can give you some amount of like some efficiency. So these are the structures, and people also started using different structures for actually increasing the stability. That we look into that. This is the major drawback of perovskite solar cell, and it is very sensitive to moisture, and it degrades when exposed to moisture. So people started actually using what is this? Starts writing. Someone is sending me annotation request. Okay. So this these structures are very robust, and but they suffer from the stability issue. So how does this actually work? So you have a N-type TiO2, you have a perovskite layer, you have a spirometallite film, you have a gold counter electrode, you have a transparent FTO. So when the sunlight enters, the work of FTO is to allow the light to pass through it. So here, if you use again a metal contact, you cannot actually shine the light on the cells. So people here go for transparent conducting oxides, either FTO, fluorine doped tin oxide, and or ITO, indium doped tin oxide, as transparent conducting oxides. And the TiO2 is a semiconductor which absorbs UV rays, UV light, and allows the visible to pass through it. So it's a wide bandgap N-type semiconductor. Then we have a perovskite layer, which is a light harvester. It actually absorbs light, and it is converting that light and creating. It is using the light to create electron hole pair. Then we have a supporting spirometallite layer, which is which acts as a solid electrolyte, and we have a counter electrode. So as soon as the light enters, the electron hole pair, which is generated in the perovskite layer, uh, actually dissociates, because the electron here actually sees the lower energy of the TiO2's conduction band, and the electron actually dissociates. And we have to also know that the dissociation energy for this electron hole pair in perovskites is pretty less. So there is no need of any additional energy, and that's the reason people would do HTL free cells. You can either make junction only with perovskite and spiro, or with perovskite and TiO2. So the dissociation energy for perovskite, the electron hole pair dissociation energy is also pretty less, or we can call it as binding energy, is very low in perovskite solutions. So this electron, because of this low binding energy, the electrons can move towards TiO2. From TiO2, it is again moves towards the FTO. From FTO, it can actually drive some load, and the electron can for the counter electrode. The electron will reach the counter electrode. The whole here, actually, the whole is not a physical existence. So it's just for understanding the electron. They call it electron transport layer, then they call it hole transport layer. Immediately when this is generated and this electron dissociates from this electron hole pair, the spirometallite, which is a electron rich material in the valence band, it actually regenerates this perovskite. It actually fills the hole immediately. So all these things happens pretty fast. and it's not actually this electron only comes and it fills it. By the time it dissociates, there is some filling from perovskite, so that this electron will not fall back to the independent hole. So it actually, this electron should be collected outside and it should drive a particular load. So this is how it actually works. And the robust, most important thing is this perovskite solar cells can be made with simple spin coating. So you can take two precursors, you can mix them together and spin coat and just anneal them at very low temperatures of 100 degree, 115 degrees, you can get a perovskite film. Or you can make individually drop precursors spin coat and individually like use anti-solvent, different solvent, like here they use DMF, here they use isopropyl alcohol. Then even then you can form a perovskite film. You can also evaporate both your precursors together, which is called co-evaporation. You can evaporate one after other and make it react, that is sequential deposition. Then you can actually make a inorganic film. You can make a PbI2 film and expose it to MAI organic vapors. You again get a perovskite film. So these perovskite films can be formed with various different techniques. Right now there are more like huge amount of techniques, and depending on the cost, depending on the scalability, depending on the reproducibility, people have adopted various techniques, and whatever techniques works in one particular environment will not work in different environment, because these are moisture sensitive, humidity sensitive. And so every lab, every research group has their own techniques, and it can also be fabricated with advanced techniques, like you can use bath deposition, you can use jets, you can use metric rod coating, you can use Doppler blading, and slot casting, spray coating. You can actually make solutions of perovskite and spray them. You can spray them on films. You can use screen printing. You like, if you want like patterning, or you can particular patterning, you can use screen printing to form them. You can use inject printing, and depending on the cost and requirement, people, it can be scaled up into, you can use different advanced techniques of thin films to fabricate this perovskite films. However, the main drawbacks of perovskite, whenever it is exposed to moisture, it breaks down into its initial precursors. And to control this problem, people have used different types of sealants and all this thing. But again, it increases cost and creates other problem. So the main drawback, this is exposed to moisture. This is degrading. Now the people have researchers have tried to avoid this degradation by changing the combination. People are going for 2D perovskites, 1D perovskites, 0D perovskites, and using different. See, this main degradation happens because of this organic part. So people have started replacing this organic part with inorganic part. So it is like they're using CCM, so CCM lead triiodide. So like that, people have started doing, but efficiencies are actually coming down. It actually comes down. People have started using double perovskites and different technologies as such. And if you see most of the perovskite, whatever we saw in the slides, had this lead. So this lead is again carcinogenic. So it causes cancer, and many countries actually uh, uh, like strictly avoid lead and regulate it properly. So this toxicity is also a problem. But so people have started replacing lead with tin and other stuff. But however, the efficiencies with lead is not achieved with other materials because of the orbitals, the 6s valence orbitals of lead. And the next drawback is the cost. When we analyze this cost, if though the perovskite cost is around 0.038%, using gold is around 18%, TCO is around 43%, again HTL is around 33.97%. So if you want to further reduce the cost, of the research has gone in a direction of replacing gold with carbon. So when you replace it carbon, you are almost neglecting, drastically reducing this part. Then replacing this spirometide with inorganic HTLs, like nickel oxide, copper thiocyanate. So using some inorganic part, you can again reduce this HTL cost. For TCO to reduce, which is the maximum amount of cost, people have even tried metallic grids. So instead of using fluorine doped tin oxide compact film, you can make a very fine metallic grids, which will act as a substrate and which can also allow light and collect electrons. So then the encapsulation is also around 0.12%. So this encapsulation cost here, it's considered because uh, it, uh, it needs that moisture stability. However, now that people have replaced perovskite itself, so this encapsulation cost has like it's also negligible. Yeah, encapsulation cost. And with this, I think I will conclude. So around 25% of efficiency is achieved right now. And silicon-based tandem cells in multi-junction around 30% is feasible. It's also 28% is achieved. And thank you for all your time. Vicky, it's open for any questions and discussions.
Thank you, sir. Participants, now the floor is open for the question.
Hello, sir.
Hello.
Do you hear me?
Yes, yes.
Yeah. So it's a wonderful talk. So, my question is on stability issue. So, stability issue is a major issue we are facing in perovskite, right?
Yes.
So, how can we solve like it's sensitive to moisture and it's sensitive to UV light or like in temperature also. I mean, thermal degradation also happening. So, how can you solve this issue actually?
So the main issues when you see right now, people are looking for different perovskites. People have started moving towards 2D perovskites. See this perovskites, whatever this happened in last 10 years. Now people have realized though we are getting very high efficiencies, we cannot use them. We can really not use them for real-time application. So we have to remove lead, we have to remove the moisture. So in that case, we, people are moving towards double perovskites, CS, DI, or that combinations. So people are moving towards double perovskites. Some people are still believing that this will work and working on encapsulation technology and things like that. So we have to change the perovskite. So changing the perovskite, people are trying to achieve latest papers. They have achieved around 1.5 years of stability, but the perovskite has changed. So once the perovskite has changed, the efficiency has gone down to again 14%, 15%.
Okay, so my second question is, uh, can you comment on lead-free metal halide perovskite? Because
Lead
people are
free.
lead-free, yeah.
Yeah,
So,
lead free. Lead free. The main problem is lead is very good for light absorption. Actually, when you see look at the orbitals of lead, the 6s valence orbital, and that orbital is what in perovskite is actually like making the structure robust for solar cell application. It can absorb light. But when you replace this lead with tin, people are replacing with so many different materials. In double perovskites, people are replacing with silver, with bismuth, and different things. So when we replace this, that high efficiency is again goes down. And when you replace this lead with different material, the cost of manufacturing increases because the precursors of lead can easily dissolve in this polar solvents, whatever for fabrication we are doing. Those precursors are mostly insoluble. You have to add something more to them, and again the cost will increase and making the technology very viable and very low cost. Again, that purpose will again be like not solved. We'll again go back to ground level zero. So it is still the research is going on. Like you have to. It's a game between stability, efficiency, and lead. So you make a structure which is free of all these things, the efficiency will go down. To make something which is having very high efficiency, again your stability will go down. Or if you balance this, again your cost will increase.
okay, okay, sir. Thank you.
Any other question from the participants? Okay, so if there is no further question from the participant, let's thank our.
Hello?
Yeah, hi. Yeah, hi.
Yes, sir. Uh, Thank you for this wonderful talk, sir.
Yeah,
Uh,
sure.
Sir, I have a question regarding the efficiency of the solar cell. Is there any theoretical limit on the?
Yes, yes. I'll just show you that side. So this is for terrestrial application with single junction. When you see this is called short peak Weser limit. So short-wave and quasar theoretically calculated if all the photons which is incident on the terrestrial application, like on the territory of Earth at the sea level, with this possible band gaps, the maximum for terrestrial application you can achieve is around 34% for a single junction. And considering one photon is generating one electron volt. If you can have multiple generation, multiplications and things like that, you can actually increase the efficiency. And if you're making multiple junctions, you can again increase the efficiency. So that's the reason in the NREL chart, we have seen efficiencies 44%, 46%. So around 33, 34% is the short-wave quasar limit for terrestrial applications at sea level.
Yes, sir.
Any other questions? Okay, so if there is no any further question, let's thank our speaker. Thank you, sir,
Thank you so much.
presenting your research work in such a short notice, because our speaker actually fell ill. So this is for the participants. That's why on such a short notice, Dr. Vishesh has actually agreed to present his research work. So thank you very much
Thank you. It
for
was a
presenting
nice
your work.
opportunity also, and nice opportunity for me also, a good experience. And I hope it was good. And thank you
Yes.
thank you for actually inviting me. Thank you so
Yeah,
much.
definitely we enjoyed your presentation. Thank you. Thank you.
Thank you.